Okay, so the very last thing I wanted to talk about before we get to the Einstein equation, so the actual field equation in general relativity, is to return to this equation of motion for particles, the geodesic equation, because now we actually know what the metric must look like, even though we haven't shown that it's a solution to the Einstein equation. Just by symmetry arguments, we know what the metric is. And so remember, if I now write out the geodesic equation for some particle which has mass, it looks like this. And I know what the metric is. I know that g mu nu can be written as -1, and then I have this three-dimensional metric here. Let's stick to, just like Dodelson does, let's stick to the k equal to 0 case for now, just for simplicity. If that's the case, well, then what I get here is, in Cartesian coordinates at least, just a squared here, right? I could write it out in polar coordinates, then I get almost the same thing. It's just I get an r squared here, and then I get an r squared sine theta squared here. But other than that, it's the same thing. And zeros everywhere else. But I can take this form of the metric tensor, then I can do all the derivatives that are needed to calculate all of the Christoffel symbols. I won't bore you with the details. It's not really all that super important. You can do it yourself if you really want to, and we'll also have exercises later where you sort of need to do it anyway. Okay, so let's now look at the zero component, so what you would call the energy component of the geodesic equation, right? So let's just write that out. So this is now a 0 here. Oops, like this. And now I already made a simplification. I'll get to it in a second. Okay, so I and j, or any other Latin letter in the definition of Dodelson, always are either 1, 2, or 3. So they always denote spatial components, whereas mu, nu, whatever Greek letters, they are always 0, 1, 2, or 3. So these are like 4 vectors, right? These are normal spatial 3 vectors. And the point is that the Christoffel symbol, which is 0 and which has any 0 down here, goes to 0, right? So you can show that explicitly, of course, but that means that I only need to take into account the spatial derivatives here, never the time derivative, or not derivatives, but the spatial part of the Christoffel symbol, not the time part. Okay, furthermore, as Dodelson also states, these Christoffel symbols can actually be written out. The only terms that enter is through the time derivative of the scale factor, and then you see it's proportional to the metric itself. Now, one other thing that I'm using, at least in my derivation in the notes, is that I use the 4 velocity. Remember, that's defined in this way. So we can rewrite this as an equation of motion, if you want, or a differential equation for the 4 velocity rather than the spatial component, right? So that would be du naught d tau plus, and this is now the 3 velocity, right? So it's this either 1, 2, or 3 here velocity. So it's a spatial velocity. Okay. So if we look at the particle that has mass, Dodelson does the case of 0 mass, but let's look at a particle that has mass. So now let's write out the square of the 4 velocity. Remember, so that's this thing here. remember last time we discussed the normalization condition for the 4 velocity and figured out that it's -1. And that means that there's a relation between the time component of whatever I'm writing here and the space component of it, right? So I could write this as this. So now I have the spatial component here and the time component here, and they must sum up to -1. And that means I can now do a differential, right? So I can now if I just do a differentiation here, right, then I get 2u naught du naught, and here I get 2u du, and then I divide by 2, and this left-hand side derivative is explicitly 0, of course, and then I move this to the other side, and then I get this equation here. And that actually means that I can now rewrite the geodesic equation into a slightly different form, as Dodelson also does. Okay, so what I get is this. And now I'm almost there. The only thing I now need is I need the relation between coordinate time and proper time, but that's given by u naught, because by definition that's the coordinate differentiated with respect to proper time. So the 0 component of that, of course, is coordinate time. So that gives me this relation. That means I can now do the derivative with respect to coordinate time, just like I have here. And then in the end, I get this differential equation for the 3 velocity. And now I'm almost there, because if I integrate this, then I find, because of the minus sign here, that the spatial velocity, the 3 velocity, the magnitude of that goes proportional to the scale factor inverse. And by definition, the form momentum of a particle, this is true in special relativity and in general relativity, the physical momentum is equal to the mass times the 3 velocity. And I can now use that because this is a constant. So that actually means the spatial part of the physical momentum of a particle redshifts as scale factor to the -1st. So this is actually a well-known result, I guess, to most people. Maybe you don't recognize it at first, but remember that we have the phenomenon of cosmological redshifting, right? We know that as the universe expands, photons redshift. And we know that the scale factor and the wavelength of a photon are proportional to each other. But then remember that the momentum of a photon is proportional to its wavelength to the -1st. And that means that this becomes proportional to a to the -1st. So this is true for a photon. But actually it's also true for any other particle, whether it has mass or not. The only effect of the equation of motion, or on the equation of motion of the expansion of the universe, is that it leads to a time dependence of the momentum of each and every particle. So even massive particles will redshift when the universe expands. It's independent of whether they have mass or not. It's a completely general result. You find also the same result in a curved universe. It's exactly the same thing. And when you think a little bit more about it, it's kind of obvious that this is the only thing that can actually be encoded in there, because normally the equation of motion has 4 components. But of course, if you do the derivative of any of the spatial components with respect to time, that cannot really change, at least it cannot change in direction. How would it, right? So any free particle that propagates in an expanding universe must propagate in the same direction for all eternity, because anything else requires some force in some direction. And that's impossible, right? Because everywhere is the same. So the only thing that happens is that the magnitude of the momentum redshifts, and therefore the energy also changes as a function of time. So really, if the cosmological principle is obeyed, this is the only effect that gravity has on any particle.